Hello, everyone. Thank you all for coming. It's like a real pleasure to be here. I haven't had the chance to attend this conference before, so I'm really stoked to be here. And it's also the first conference that I've ever managed to attend where I was in a holographic form. So hopefully this should be quite interesting for those who are viewing it in the other room. My name is Ben Stopford. I work at this company called Prevalent. We're one of the companies that sits behind Apache Kafka, which is an event streaming platform. And the company was originally set up by the founders. The founders of the company were originally at LinkedIn, and they built Kafka, and then they sort of set a company up around that. And that's kind of where I work. And I'm actually an engineer by trade. I've been an engineer for about 20 years. I've spent about 2 years working on Kafka itself. I built the replication protocol, automatic data balancing, or at least the latest version of the replication protocol, and a few other things. So that was kind of like my background. But these days I work in this office of the CTO, which is a slightly different role. It's a little bit broader. And one of the things that my team does is we look at the industry and we see look for what the big trends are and how they're affecting our customers as well as other people in the industry, and how these things kind of fit together. And today, although I'm going to talk a lot about event streaming, I also want to talk a little bit about how these rather disparate parts of the industry come together and why that kind of matters for you guys. So if you look at infrastructure technology, there are a lot of different categories out there. I mean, you're all familiar with relational databases. They've been around for 50 years. They've been the building block, the cornerstone of probably most of the applications that you build today. And from them, a lot of other technologies have arisen. So we have data warehousing, which is in many ways a kind of reformatting of that original relational database to suit a read-optimized workload. So where we're collecting data from different parts of the company and reformatting it so that we can access it quickly and do like complicated queries, reports, etc., etc. A little bit later came messaging. So messaging is not really a data technology. It's a piece of infrastructure which helps one application communicate with another one. But it actually came with some really nice sort of patterns and paradigms that sat behind it. You can send a message out and have many different people subscribe to that message. You can also do things like create queues, which allowed you to build richer applications, or even actually richer, better connected companies. Then there was like a funny little field that emerged in the 2000s called complex event processing. Anyone ever done any complex event processing? Getting a few hands there. So it's a little bit more niche. It was mostly around the finance area. And this technology was interesting because it was the first time that we actually had a technology which focused specifically on dealing with data as it moves around. So you think of what a relational database does, it deals with data that's at rest. You collect your data, it accumulates, and then you run queries against it. This was kind of the first thing that actually dealt with data that's happening right now. And that's like a little bit different. In the mid-2000s, we kind of got the internet, right? So we had to build systems that had much more scale. And that led to big data, NoSQL, a variety of different infrastructure components that are able to scale to many different machines. And then we have event streaming. So event streaming actually pulls from pretty much all of these different fields. So from a relational standpoint, from a database standpoint, you can actually use a SQL query against an event streaming platform. It actually even includes things like transactions that allow you to do these things at scale. It also relates back, though, to this idea of complex event processing, because it's not just about accumulated data. Although you can accumulate data in an event streaming platform, it's actually about reacting to that data in real time, but using a similar type of dialect. And then there's another big categorical change that's happening at the moment, and that's cloud. And actually, in more contemporary terms, or more recently, serverless. And serverless is, although it's kind of an evolution of cloud, it's actually something a little bit different. And I think it's going to really change the way that we write programs. And the interesting thing about these two different categorical changes is that they actually relate pretty closely to one another. So Kafka at its heart is a messaging system. So you can use it pretty much like you used a messaging system back in the 1990s. But it has like a number of unique properties. The first one is it provides a sort of unprecedented level of scalability. You can have like hundreds of machines. So if you look at the back ends of Apple or Uber or Netflix, you'll find these massive streaming platforms which are absorbing very large amounts of data coming from the internet. It also is able to store that data. In some ways, a bit like a database does, but it has a very different way of interacting with it. So you can store like hundreds of terabytes of data inside an event streaming platform and replay that information. But the final differentiator is this ability to do this stream processing. And this is, again, very similar to the way that you interact with data in a database. It can use tables, actually much like you can in a database. But it's really focusing on this data which is moving in real time, allowing you to build applications that really react. But if we go to the real essence of what's changing, from a programming perspective, is probably this concept of an event. This sounds like a really innocuous thing, right? It's just a fact, some observation about the world captured at a point in time. So you waking up this morning at 8 a.m., that's an event. Right? You come into this conference, that's like another event. In a business context, it's like a payment, an order, a page view, a log line, a sensor reading. All of these things are just events, things that happened in the past which some system has observed. So that maybe doesn't sound that fundamental. But when we start to build these concepts into our architectures, we get some pretty interesting things. So events actually come in streams. This is effectively a time series. An event isn't just like an isolated thing. So you getting up in the morning and then you having breakfast. This is an event stream that describes your day. And to understand your day, you actually have to look at all of the events. You have to look at the stream itself. So streams are interesting because they let us react to data that's happening in real time. But they also let us extract some context from that stream. A stream processor is able to keep context, which is about stuff that's happening now, as well as stuff that happened in the past. So this might be something like a stock price fluctuating over the day, and you wanting to do something with that information in real time. Or it could be a business system, where an order is created, it goes to being confirmed, it goes to being paid, and then maybe it goes to being shipped to your door. These are all just time series of events which we can react to as streams. So a stream processor is a tool that's basically built for this particular world. It allows you to take these event streams in, react to them, combine event streams from different places, or do lookups in tables. You filter that information so you actually get exactly what you want. Summarize it over time, so you might just want an end-of-day price or something like that. And then emit this information to some other, maybe like microservice that you want to consume in some language of your choice. So this is a little bit like a database in some ways, but actually fundamentally about being real-time. So if you embrace this concept of events inside your architectures, your programs kind of change in two main ways. The first thing is the way that you actually go about storing data. And you don't actually have to implement any of these patterns, but these are the sort of benefits that you get from doing so. And the second one is the way that your programs actually communicate with one another. So let's look at this first one first. How do you store data? Well, I would like to start with like a very, very simple example. You've all probably built at some point some kind of website, or at least been on one, and there's a shopping cart. So here we have Bob's shopping cart, and Bob has a pair of trousers, a jumper, and a hat. And the system stores that data in a database. So what's the table going to look like? Well, it's probably going to look just like the shopping cart. It's going to have a row for trousers and a row for jumpers and a row for hats. And if Bob decides to order another pair of trousers, it's just going to increment the value, update the value, and so we actually have maybe 2 pairs of trousers. So you might wonder, well, what's wrong with this architecture? The answer is actually nothing. We've been building systems like this for as long as we've been building shopping carts. But there is an interesting observation to be made about this very simple use case, which is that if we thought of it in an event-driven way, the events actually create a time series of things that the user did. So in this particular case, Bob actually added 2 pairs of trousers to his shopping cart. Then he added a jumper. Then he realized that he didn't want 2 pairs of trousers, so he removed one. Then he added a hat, and then he actually went to check out. So the events, because they actually record what really happened, what the user really did, this describes this chronology of the system. So actually, we have more information here. So if we store data as a stream, if we store data as a chronology of events, we actually retain all of the information. We get a journey that describes exactly what the system did. And importantly, we can always derive that current state. So on the right-hand side, we have like the traditional view in a database, where we actually update values and information is lost. But we can always derive our current state view from the stream of events. So we can store this in a database, we can store this in Kafka. It actually, at this point, makes no difference. We can always derive that. In a database, you could do it with the materialized view or a trigger. In Kafka, you would actually typically do it with the stream processor. Or if you've ever come across the field of event sourcing, you actually often store these things in a database and just apply a projection in your own code. So if you chose to take this approach, there are kind of three main benefits to having this type of storage model. So the first one is kind of like a business lens, right? Because we're actually capturing everything, and because Kafka maintains data in a way that is immutable, and we actually have an immutable audit trail of everything that's happened. And that's more than just keeping some audit trail somewhere. Actually, the data model which underlies our system is by definition immutable. And yes, before somebody asks, you can solve GDPR, but you have to do it a slightly different way. But the sort of philosophy behind this is that accountants don't use erasers. So you kind of want to have a data model that actually captures exactly what happens in the system so that you know what happened. And you know this if you're a programmer because you probably use like Subversion or Git or some kind of source code repository tool which gives you the history of exactly what your file did. This is like the same thing for data. The second benefit you get from using events as a sort of storage model is replayability. Let's say you have a bug in your code, and maybe you've got like the icon on your shopping cart wrong. That's like pretty easy to fix, right? You just go and change the image, and you're done. What if you have a bug in your code which actually creates some corrupt data? Or what happens if you have a bug in your code which creates some data and sends it to another system? And that's actually a little bit harder to change. So you can go in and change the code, but you've actually got this corrupted data. If you've got the indelible source of truth in your underlying data model, then actually you can just rewind back in time to the point where you had your programmatic error, when that programmatic error was introduced, and you can just replay, and it recreates the data as it should have been. The third lens is this analytic lens. So when we build systems today, often we'll start off building some kind of web application which deals with users, and we're normally just trying to get stuff done. But then later, we want to be able to sew in some kind of analytic system which actually looks at what users are doing. Maybe it's doing things like fraud detection, or maybe it's trying to suggest things. And for those kind of analytics tools, particularly ones that involve machine learning, you actually need this complete data set of everything that the user was doing. So this event-driven model marries very closely to that. So what do such systems look like? Well, actually, they look like lots of different things. There are loads of different incarnations of these patterns. We see them in event sourcing and CQRS. We see them in streaming systems. Here's just one that I thought I'd share with you. This is not like a traditional big data Kafka use case. This is actually the architecture of the New York Times website. And it's interesting because, I think it's interesting because it's actually a more traditional system. This is effectively a content management system. So on the left-hand side, authors write content. They create images, they write bylines. And all of this information that they do that they create to push data onto the New York Times website gets stored in a single Kafka topic. It's called the monologue. And that is effectively their source of truth. It's every piece of information which they've created since 1851. And that data is then streamed into this denormalizer, which sits next to it. And that's actually a Kafka Streams application. And the job of that is to take this immutable record of everything and turn it into something which actually makes sense to present to a user. So they're separating the storage, the event-based storage, from the view which a user actually sees. So this is actually effectively like a messaging system because it's allowing you to update this data in real time. The content view is being created in a set of additional Kafka topics, and then that gets pushed into Elasticsearch, which actually serves that to the website. And the interesting thing about this kind of approach is that if they want to change the view, or maybe they want to add a new view for like an internal website, they just change the denormalizer, they rewind the log, they just replay those events which form their source of truth, and they just create the view that suits like the new version of the website or whatever it is that they want to do next. So if we go back to, so that's a little bit about how events kind of affect the way that you store data. But events are actually about much more than that. They're also about the way that different applications communicate with one another. So you probably are building some kind of system today, I would imagine. And it probably sits somewhere on this chart. It could be a monolithic application, like a single app server with a database. Maybe you go for a distributed monolith, like a bunch of different application servers that have like a database that they share. Maybe you like microservices. So microservices, each service has its own database. This has like pros and cons. It allows you to basically separate the data from different services so that they can effectively release themselves in a more independent way. It gives you better decoupling. And this actually makes a lot of sense when you're building front-end systems. So if I have like a user interface, that user interface maybe calls out to like 10 or more different microservices which like respond back in real time. Where event-driven microservices tend to come in is where you actually want to do things which are decoupled from that front end. So let's say I want to do something like fraud detection. Or maybe I want to start executing the process to send some item which someone ordered to their front door. Or alternatively, maybe I just want to send them an email. I want to do something, but I want to keep it decoupled from that front-end architecture. That's the normal starting point for this event-driven world. So my front-end services simply create events. And there's actually lots of ways of doing this. You can write to Kafka directly. You can use change data capture. There's a whole variety of mechanisms inside a streaming platform that makes that easier. But what we end up with is a bunch of events in Kafka. And then from those, we can subscribe to them and build our decoupled services for whatever those things, those use cases may be. And then as these architectures grow, it's actually quite nice. Because we've decoupled ourselves from the front end, we can like plug in new services. So if now let's say we want to build like a recommendation engine, or we want to push data into some data warehouse, or whatever that might be, we can just kind of plug that in to this event streaming system and push the data into whatever it is that we need to build next. But the sort of final twist to this is that an event streaming platform is more than just a messaging system. It actually has the ability to deal with data in real time, very much like a database does. You can join, you can filter, you can transform, you can enrich events in real time. You can actually summarize them. So you might be able to, summarize some value over the last hour, the last second, the last day. So we can actually use the streaming platform not only to decouple, but also to prepare that data. So why would we want to do that? Because it actually makes it, again, easier for us to plug new things in. So our goal as a programmer tends to be to make it as easier for us to build a piece of technology and actually get hold of the data that we need. And in this world, we're trying to do this in as real-time way as possible, so we can be as reactive as possible to our business. So the kind of key point here is that we want to make the consumption of real-time event streams as easy as possible, even if the data is coming from a whole variety of different places. That might be different places, different applications in a company. It might be different databases. It might be different microservices. But as we start to build these architectures where we have many different event streams, we need some way to reason accurately about them in what is actually an asynchronous world. So in this view, we can think of a stream processor as really being a kind of database. It's a kind of streaming database really designed to create new event streams. So to be a bit more concrete, I might have an order service, which creates orders, a payment service, which creates payments, and a customer service, which unsurprisingly creates customer events. And these events are being published. And we don't know where they're going at this point. We want to add something new. Well, we can use a stream processor, and that will prepare this data, sort of bind the payment together with the order and bind that also to the customer information. That's actually two streams in a table, for those who are a little bit who have a better understanding of this kind of topology. And actually here we're going to do something really simple. We're going to send an email. But the important point is that actually it's very easy for us to build this. Like the application itself literally just listens to this event stream. It's actually got all the data in it that it needs already because it's defined that in a query. It just reacts to an event. It's got the payment. It's got the order. It's got the customer information. Sends the email. So this is why I wanted to talk a little bit about serverless functions. Because this other movement that's happening is also quite interesting. Because it is also event-driven, but in a slightly different way. So what is a serverless function? Anyone here use serverless functions in production today? There's a few of you. I think a lot of people think of these as being like slightly toy things that maybe they could just like add on if they happen to be running in the cloud. But this is actually quite an interesting paradigm shift in the way that we write programs. And this is quite easy to overlook. So a serverless function is just a function, right? You can write it in a whole bunch of different languages, just like you might write a function in the programs that you're writing today. And the canonical example of this is like resizing images, right? So let's say I have a bunch of images and they're in an object store like S3, and I write an image to this object store. I have like a little process which would run and maybe resize that so that I have a thumbnail. So maybe I don't want to have a server that I run myself to do this process. I just want it to happen. I write it to the object store and it just happens. So a serverless function lets me do that. I can like write a little function and it does the image resize. And the interesting thing about it is that every time I like write a new image to this object store, the function, it'll just automatically spin this function up in a little container, resize it, and off I go. The other interesting thing about it is it actually has inbuilt parallelism. So if I write like 1,000 images to this object store, I actually get like 1,000 functions at the same time, and they'll run in parallel. So I can actually get this very nice throughput. So to do this, I simply write a function, I upload it to my cloud provider. In this case, it's image resizing. I configure some kind of event trigger. That was an object store-based one, but we can do this from using a connector from Kafka. We can do this just by hitting an HTTP event endpoint. We can do this from a database, or we can actually configure timers. And the key point is that it's fully managed. There's no server that you run. You're completely abstracted away from it. And actually in there comes both benefit as well as problems. But that's a longer story. But the benefits of these serverless functions are worth drilling into. Right, so the two nice things that they have, the first one is that they have this auto-scaling property. Right, so I can have like 0 or 1,000 functions running concurrently, maybe more on some providers. And these will actually react to the load. So if there's like a big backlog, because at the end of the day, these things are completely event-driven. If there's like 1,000 events waiting to be processed, it will just scale this out. And the second thing is that you get this like pay-for-execution model. So because it's event-driven, we can get this auto-scaling, and then because we're actually only using these resources for the time it takes to react to this event, we're actually only paying for the bit that we use. So whether or not we run like one function 1,000 times or 1,000 functions concurrently, it doesn't cost us anymore. So serverless programming is actually pretty interesting, and it's likely to become prevalent. It's probably going to actually affect most of us in the future. And one of the reasons for this is that it's actually, it has like a lot of backing behind it. Like the big cloud providers, they're all very wedded to this. They're all very keen that you should continue to use this type of paradigm to run your programs in the future. What's kind of missing is actually the integration. Like we're starting to get like IDE integrations. We're starting to get better tooling around this world, which kind of makes it easier. But it's very much likely that we will not be running our own servers. It's very much likely we probably won't be running our own Kubernetes clusters in the future. We'll outsource that problem to somebody that has better competitive advantage. But the interesting thing about serverless functions, at least from the point of view of this talk, is that they are event-driven. At their core, they're actually based on a stream of events. And that's what's driving this like auto-scaling functionality. But they're not streaming. So what do I mean by that? Well, let me continue this sort of simple example where we have the customer service, the order service, and the payment service. Like, if I was going to solve that problem again, I'm trying to send an email. I need to know that an order happened and a payment happened, and they probably happened about the same time. And I need some customer information so that I know where to send it to. Well, to do this in a default way, I'd like react to these events, and I'd probably just put them in a database. And that data would be stored there. And then I might decide that I'm actually going to drive my event-driven program using this function from the payments source of events. Okay, so I create a new serverless function. That now can read from the database and do its thing and send out this email. But even this simple problem is actually a little bit more complicated than it looks. Like, because my order and my payment could arrive at different times. I have to worry about the ordering. And then I need to reason about that in a way that it's actually going to make my program accurate. So a stream processor actually solves these problems for you. It acts as a kind of data layer for these serverless functions. So instead of doing all of that piecing together inside a set of functions, we can actually prepare this data so it's exactly the right shape for us to do our invocation. And what's actually happening here is we're moving the stateful operations that we'd normally do in a database into the serverless function, into the stream processor, which can actually obviously be running on the cloud. And then we're using the fact that the event stream, the enriched event stream, is actually stateless. A stream of events is always stateless. To bring the data to our functions. This gives us very good elasticity. So this pairing is very interesting. So we've covered like a few different things here. Let me just summarize. So events themselves are a sort of simple concept, but they underpin the storage models of truthful and factual systems. So if we record events, then they give us a very good basis for us to build basically everything else, whether that be a front-end system or like a complex analytics platform that uses machine learning to do whatever you need it to do. Secondly, events decouple architectures. So if we have like a number of different systems, we can plug new things in. So if we think about this like increasingly serverless future, which is quite likely to happen, it is itself inherently event-driven. Events make things auto-scale. That's what facilitates that process. The same is true of pluggability. Our ability to plug new things in is the thing which makes these kind of ecosystems work, because we have a number of different technologies, and we need them all we need these ecosystems of technologies, which are often quite fine-grained, to be able to evolve independently of one another. And the same is true for pay-for-use. The model, again, facilitates this ability to only have to actually consume the resources that we need. And then finally, stream processing provides this interesting conduit in which we're able to prepare our data sets using this kind of streaming database, which is designed specifically for these aspects of this event-driven world. And that's all I wanted to say. Thank you very much for listening. My name was Ben Stopford. You can find me on Twitter. We have like a Confluent Cloud, which is like our cloud implementation. There's also like a book which talks about a lot of these underlying concepts of event-driven systems. And I'll be signing some of those over on the Confluent booth. It's just about there, I think, just in the other room. So please come over. It would be great to get to meet you all. And thank you very much for your time.